As you've probably noticed by now, understanding how electrons are shared or transferred between atoms is an important key to determining what sort of bond you're dealing with. To recap, let's compare ionic and metallic bonds to relationships between roommates. Some roommates share everything so equally, it's almost like no one owns anything. That's like your metallic bonds, which share electrons like roommates share pizza. Some roommates borrow your stuff and never give it back. That's like an ionic bond, where one atom steals electrons like a bro steals your food. There's no sharing going on in that relationship. And then there's covalent bonds. That's what's up next on PS100. The Latin roots for covalence mean shared valence or shared strength, which is great because sharing electrons is what gives covalent bonds their strength. Covalent bonds always share electrons in pairs. Single bonds share one pair, double bonds share two pairs, and triple bonds share three. Quadruple bonds are rare. There's just not enough room between atoms to share that many electrons when they're close enough to bond. Some atoms attract electrons better than others. We call this attraction electronegativity. When one atom in a molecule is more electronegative than others, the shared electrons spend more time around it than other less electronegative atoms. And when the negatively charged electrons hang out more on one end, the molecule gets polarized like a magnet. Since polar bonds have two poles, a positive and a negative pole, we call this sort of molecule dipole, which means two poles. If the atoms in the molecule all share the electrons equally, on the other hand, we say that covalent bond is nonpolar. To be clear, both polar and nonpolar molecules are neutrally charged. One side may be more negative and the other more positive, but those two sides balance each other out. Within either a polar or nonpolar molecule, the more electrons the atoms share, the stronger their bond, and the harder it is to break those atoms apart. Once these bonds are formed within a covalent molecule, interaction between molecules can begin, and they can start sticking together. Let's take a look at three ways this happens. First, you've got dipole-dipole interactions. Like a bunch of magnets, the oppositely charged poles on the dipoles stick together. Then you've got hydrogen bonds. These are really just a specific type of dipole-dipole interaction. They're stronger than your average dipole-dipole, and here's why. Oxygen atoms are much more electronegative than hydrogen, so when they bond to form water, the dipole that they form is extremely polarized, which means the opposite poles of neighboring molecules are strongly attracted to one another. Even though formaldehyde is also a dipole involving hydrogen and oxygen, you've got a carbon atom stuck in the middle. This keeps the oxygen from hogging the electrons so much, and the polarity is less strong. Consequently, the dipole-dipole interaction between two formaldehyde molecules isn't as strong as the hydrogen bond between two water molecules, so they're easier to break apart. Finally, you've got dispersion forces holding together nonpolar covalent molecules. As electrons are always changing position, even a nonpolar molecule will temporarily become more positive on one end and more negative on the other, so opposites can attract between them as well. But as you can imagine, it's pretty easy to separate molecules held together by dispersion forces. They're the weakest of these three interactions. One word of caution before we wrap up. Don't confuse these interactions with covalent bonds. There are three ways covalent molecules can interact, but covalent bonds are formed between individual atoms to form molecules. Also, the covalent bonds within a molecule are stronger than any interactions between molecules. So when you boil water, you're actually breaking the intermolecular forces between molecules, not bonds within a molecule. That's it for this episode, but thanks for watching. And you'll find more science and research opportunities for BYU undergrads in the description below.